Okay, so we were actually discussing maybe the parameter estimation. Especially, we have actually seen the what is actually the maximum likelihood estimation. Okay, and we have seen MAP method also. So where we are actually finding out one best value. Okay, so that means we are assuming that that parameter that we actually finding out. Okay, which is the theta cap, maybe by notation is actually the best value which will actually maximizes the probability. And so that is actually the maybe the estimation that we have actually discussed. And here we will see another method. Okay, so which is actually the maximum likelihood estimation we have already discussed. So the next one is actually the Bayesian parameter estimation, which is actually maybe conceptually different from what we have discussed. So here we are assuming that okay, especially the theta, that is a parameter, is a random variable, and we try to find out a probability distribution for theta. Okay, and then we find out maybe the best value for theta, maybe the maximum value. Okay, something like that, and we'll be trying to see that okay, we will be taking this theta cap as the best value. Okay, so here we are trying to find out a probability distribution for theta, and then we can maybe choose any value of theta. Okay, from that distribution we can assume that but there will be one value which will actually give you the exact result, or maybe very identical result as we got for the maximum value for theta in the MLA estimation that we have discussed. Okay, so that is a one major difference between both of these two. So we will see other maybe differences later. Okay, and anyway, so this is actually the heart of this particular the most important maybe concept here is actually the Bayesian classification that we have already seen. Okay, so that means whether we are actually estimating the theta cap value, okay, by either MLE estimation or MAP or maybe using Bayesian parameter estimation. Finally, what we are actually trying to find out is actually the computation of the posterior probability. Okay, so that means you are given a feature vector x, you are trying to find out for which class or for which category that probability is actually maybe highest. So that is ultimately based on which we actually maybe deciding the discriminant function, and then maybe taking the decision, okay, or the prediction accordingly. Okay, and so if you are actually trying to bring in the concept of the data set, okay, that's a training data set, as we have already again maybe see these type of notations. So the goal is actually to compute maybe probability of WA, okay, given x comma, okay, the a training data set. Okay, so that means you are given a feature vector x and a training data set. So both of them are given, and then what is actually the probability for a given wi. Okay, so that is a maybe considering the concept of training data also. Okay, so if you are considering the training data set D, okay, then we can actually maybe the representation of the Bayesian formula. Okay, formula will be Wx given D is actually maybe, okay, we are actually trying to incorporate D, okay, along with each of the maybe the terms. Okay, that is with respect to the prior probability and with respect to the class conditional density. Okay, so that is a case. Other notations are without a D, they are actually general notations. But we are given a training data set. Okay, then what is actually the prior probability? Okay, given a training data set. Okay, so the thing is that we can actually maybe, for example, suppose we take a prior probability, we can actually have some knowledge about some prior information about a WA class. Okay, but so that we usually keep as a prior probability. But when you are actually given a training data set also in addition, then you can have a prior information about each of the category, okay, using that training data set also. So that is actually we are empirically estimating that particular prior probability once the data set is actually given. So that is a significance of maybe, okay, this particular, say, the concept of training data set is also added to maybe the probabilities. So that is actually the idea. Okay. Okay, so this is what we have actually, maybe whatever we have actually discussed. Okay, the same thing. So that means we are actually trying to bringing in. Okay, maybe so there are different cases. Okay, one is actually a probability of okay, x comma d given wi. Okay, and the probability of x given d. Okay, all these are actually we have a c. So we have a probability of x comma d, that's a joint. Okay, probability, okay, given a particular category is nothing but we can assume that a probability of okay x given d comma wi, and in the probability of d given wi. Okay, so that means we are actually assuming that okay, see, the training data set is also okay, but taken into consideration. Okay, so that's a probability for that particular case, and using that again we will try to okay, find out this one, and then ultimately we will find out these terms. So these are nothing but just to maybe bringing in the concept of training data set D is also into the maybe various definitions. I think that we have already maybe seen, and this is actually the thing that I have just mentioned. Suppose you are having a prior probability, but when you are having some additional training data set is also given, then what is a prior probability? So that is a probability of a wi given d. Okay, so that is a prior probability. The training samples actually provides this particular say data. So that is maybe the difference in notation and the meaning of each of these particular say probability terms when you are actually including the concept of training data set also. Okay, so that is a case that we have seen. Okay, so when it comes to Bayesian parameter estimation, okay, so what we are actually trying to, okay, as a general theory, how this particular thing works is, okay, so what we have to find out is, we have to find out maybe probability of x given d. Okay, so that means this is a class conditional density, okay, and that must be multiplied by okay maybe with respect to prior probability in order to find out the posterior probability, okay, that we know. So that is a base maybe the formula, but as in that we now look into only probability of x given d, we are actually trying to find out. So that means you are given the training data set, what is the probability for the class conditional density. Okay, that should be with respect to each of the category. Okay, because what we have actually seen is probability of x given wi, that is actually the likelihood, but the wi is actually we can say that we can categorize, we can group the tuples, okay, training data set into different categories. So that means w1 w2 w3, and each of them we can actually call it as d1 d2 d3 because we have the iid, okay, principle into effect. And then we can we don't need to distinguish maybe d1 d2 d3, let us say d, okay, because d is going to be independent from the other whatever say categorical data that we are having. So anyway, so the computation can be applied to any situation in which the unknown density can be parameterized. So that is actually the idea. So here, what we are assuming that the prior see when we are having the Bayesian formula, okay, decision, we have a likelihood and a prior probability. So prior probability, we are assuming that we have some knowledge, okay, maybe from the already existing knowledge, or maybe from the training data set, you can actually find out a prior probability. But the most crucial thing is actually the class condition density. Okay, then so what anyway we actually there is again a problem with this type of, because Bayesian or maybe MLE, we don't know the exact function that we are trying to do. Okay, that actually generates a particular data. Okay, that's the best one. So but what we are actually trying to do is, given the training data set, then we are trying to build, okay, we are trying to maybe approximate, okay, to a particular maybe probability distribution, so that we can actually maybe represent that particular probability distribution using some, okay, the parameters like a mean and the standard sorry, variance, and then we can have the analysis, okay, and maybe we can do the prediction also. So that is a concept. But now we are assuming that so even though the probability of x is unknown, okay, the probability of x means that is actually the class conditional density with respect to each of the classes. If that is unknown, but we assume that say the form of p of x given theta is known. So that means we are assuming that the parameters, okay, the form means whether it's a Gaussian or maybe some other distribution is actually not. So we assume that the given the parameter, okay, vector, okay, of a distribution, okay, then we can actually, okay, we know what is actually that particular form. So that is the assumption. I think that we have done in the MLE case also. So that means probability of x given theta is not, okay. So the value of theta is not known exactly, and that we have to find out. So once we know the parameter vectors, okay, the values, okay, we know what we can represent the form of the distribution. So that means Gaussian or binomial or maybe any Poisson distribution, whatever distribution, okay, of different kind, okay, and from that we can actually we can find out maybe probability of x given d. So that is a concept. We will come to this in detail, okay. And so we know that the initial knowledge of theta, okay, is known, okay, in a prior probability density as p of theta. So here we are actually assuming that we are having a parameter vector, okay, maybe for example in the form of a mu or sigma, okay, sigma square, whatever it is, okay, whether it's a univariate or multivariate case, okay, and we assume that with respect to the parameters also we are having a prior knowledge. So that is a prior density, okay, we are having p of theta, okay. Then, so once that is known, then the rest of the knowledge about theta is contained in a set of D, okay, of n random variables. That is our features x1, x2, etc. That follows p of x. So that is the assumption. So we don't know exactly what is probability of x given D, but we are assuming that probability of x given theta, that means the parameters that generated this training data set D, okay, that form is known, but only the parameter values are actually unknown, that we will be trying to find out from the given data set D, so that the problem is actually solved. So that is the assumption that we will be utilizing, okay. So with that point in mind, okay, suppose how we can estimate maybe a Bayesian parameter estimation. Assume that is the form of probability of, okay, x given d, okay, or maybe probability of say x given theta in this specifically, okay, is actually not. So that means suppose that they are actually following Gaussian distribution. So then we have to estimate theta using, okay, what we have to do is we will be defining a posterior probability of d given theta. So that means we have to find out theta, that is our ultimate goal, and we are given a training data set d. So from this, using this data set, we will be finding out okay, maybe the probability for what is theta. So that is which theta we are actually trying to find out, because once we know the theta, okay, maybe the best theta in the form of theta cap, okay, then the problem is reduced to, okay, the MLE estimation that we have discussed. Okay, that means you know what is theta cap, and using that theta cap, we can actually maybe you can substitute that values into the Gaussian equation, and then that forms a maybe the discriminant function, okay, and then the rest is actually we know, or maybe we can use the Bayes rule, okay, whatever we are actually which technique we are actually using. So that is we are trying to find out the probability of theta given d. So that is a goal actually, okay. Suppose we know the univariate case where assume that mu is actually the only parameter, okay, unknown parameter. So that means theta is actually only consists of the mean, okay, mean value. Suppose, okay, so that means we have to find out the probability of mu given d, okay. So that means mu is the only unknown parameter in this specific case. We will see the general case in the coming slides. So we are assuming that a probability of x given mu. So that means the probability of x given say theta. We assume that the form is known. So that means which form the probability takes. So we are assuming that this is a Gaussian distribution with mu and sigma square as the the parameters. Okay. And now what we are assuming is another assumption is that so we consider, okay, p of mu. So what is p of mu is actually a prior information about the mean value. Okay, the prior information about the mean value. So that is a maybe this is also a prior probability, but with respect, okay, earlier we have a prior probability of wi. Okay, so now we define a prior probability of mu. Okay, so what can be a guess, okay, for the mean value, okay, for a particular say x, okay, maybe a particular a single feature or a say multi dimensions. Okay, so that is the probability of mu. Okay, so we are assuming that that also follows. Okay, so that means I already so suppose we assume that the mu also take a probability distribution form. Okay, and we assume that that also takes a Gaussian form, and then that is going to be defined by mu zero, okay, as the mean of the mean. Actually it is mean of the mean, okay, mu zero, and maybe then sigma square. Okay, so that is the variance. So that means that is actually the case, and we are assuming that mu zero and sigma zero are not, okay, because this is something like a recursive way we are actually trying to solve it. Okay, so we started with the first one. Okay, that means we are assuming that we know what is mu and sigma. Okay, so when we define the probability of say probability of wi and probability of x given wi. Okay, so but when we do the next level, okay, so that means we go to distributions of mu. Okay, and then again we are assuming that mu zero and sigma zero are actually not. So it is a form of recursive way of we are actually extending the same say maybe concept, okay, in the next level. So that is actually the idea of maybe how we can write this particular say representation. Okay.
Sorry, sir. You have taken mu zero and sigma zero as known. So can we say that both these are considered as a constants?
No, they are actually not constant. They are actually maybe your best uh, prior information that is with you with respect to the mean value. Okay.
Okay, okay, sir.
Okay. So that is it's not a constant. Maybe when you make a guess, then that is going to be fixed there, and based on that only your further analysis will go in the upward direction. Okay. So that is again that they are going to be maybe this particular say we are assuming that is that they are not. So that non is either it can be a guess or it can be you have calculated in some way, maybe using some your prior knowledge or whatever it is. So that is a assumption. Okay, because the same assumption is actually what we have actually used in the with respect to the earlier case also. Okay, so that is now what we can do is so again we are writing the equation like this one, that is probability of mu given d. So that means that we are trying to find out what is going to be the distribution of that mu value. So this mu value is actually maybe with respect to our original base equation that we are trying to solve. Okay, but mu zero and sigma zero is actually going to be used to find this particular say mu. Okay, so that is a case, but so we can say probability of mu given d is this equation. This is a base formula that we have discussed. Okay, that is probability of d given okay, and we are assuming that this is a continuous variable, so we can say that it is integral over the the entire space of maybe say mu value. Okay, and now always we keep because here we are actually we know that d is actually a set of x1, okay, x2, etc., up to say xn. So that means we have discrete values. Okay, so we are actually not considering all the possible cases. Okay, so in that case suppose we are trying to bringing in the product of maybe the IID principle also we try to bring in. Okay, then we can say that we can replace this with the probability of xk given mu. Okay, because d is actually nothing but a set of samples. So that means we can say that and d consists of xk, okay, where k actually takes 1 to n. So that means now ultimately this equation we can say that we are trying to xk given okay mu into probability of mu, and we'll have some denominator terms and other things, and assume that we are actually representing as alpha, because we are actually not interested in those terms which will not contain any say the value of mu. Okay, assume that, so that you can maybe look into the textbook, because we are actually not going to that analysis part, but our interest is actually we can represent the previous equation in this form, and this alpha is actually going to be all the other terms that are remaining maybe while we convert this equation to this equation. Okay, and we already know that okay, so earlier, so that means we are given probability of xk given mu is okay approximate to okay a normal distribution. We are assuming that mu and sigma square, and we assume that mu is also okay probability distribution with corresponding okay mean value and sigma say 0. Okay, so that is mu 0 and sigma square is with respect to this one, and the original okay mu and sigma is actually with respect to this one. Actually we are trying to find out this one. Okay, so that is actually the idea. Okay, and we can actually substitute these values. Okay, so we can substitute all these actually okay cases okay into the previous equation. Okay, so that means we, because we know that what is probability of xk given mu is nothing but it is a Gaussian distribution, and probability of mu is also we are assuming as a Gaussian distribution. And so there's a difference. Say for example, say this is a Gaussian distribution, and from where we assuming that we will have a one maybe a mean value we have selected. So based on that we mean value we will be maybe trying to find out this whole thing. Okay, so that is one point. So if you substitute the idea of maybe say this equation and this equation okay into this equation. Okay, so then what we will the case is this previous equation, that is probability of mu given d. Okay, we can actually obtain okay so we'll get an expression of this kind. Okay, so again you can try to see it's nothing but because you can see that there is exponentiation okay comes here. Okay, so how that comes is we know that the equation of Gaussian distribution is 1 by square root of 2 pi sigma square exp of. So and okay, and similarly for okay here also we'll have, so that means we are having the previous equation maybe of this kind. Okay, so again you can see that there is alpha. Okay, and maybe we can have maybe further in cases also we will see constants which are actually not having any term. Okay, maybe of mu we will be putting all of them into maybe some constants, because that is not interesting, or that is actually not influencing the probability value. Okay, there are going to be some normalization form, or that's all only, because they just increase. Okay, because that will have an impact on any value. Okay, so that is you can say that's a normalization thing, so we can just ignore it. Okay, so this is actually the equation that you will get. Okay, so if you look into this equation also, okay, you can see that this is also maybe it's a quadratic interval. Okay, so that is a mu square. Okay, so that means you can see that when you take a Gaussian distribution. Okay, when you take a Gaussian distribution, we have a x minus mu the whole square. Okay, because you have a exp of okay so we have a we have this equation. So that means usually in a normal distribution you will have x minus mu the whole square. So that means you will have a square of okay mu value. So similarly this is also going to be xp of minus half. Okay, it will have a square term. Okay, and maybe the remaining is okay some additional term, but all these are actually forming the exponentiation okay term. So here also we can see that this equation is also okay a type of normal distribution, because now in a normal distribution you will have okay mu square. Okay, so here also you can see there is a mu square term. Okay, because it's a okay exponentiation. So that means this is a conclusion that the probability of mu given d okay it is again okay a normal distribution. Okay, it is also a normal distribution which is, let us say we write as mu n and sigma n square. Okay, so maybe the mu square and sigma 0 square is actually going to be related to this one, that we will see. Okay, but generally let us say that this is maybe again a normal distribution okay of mu n and the sigma n square. So this is actually maybe how we can say that the probability of what mean value okay with respect to the training data set is actually is also a form of normal distribution. Okay, so that is one point. Okay, so this is a same equation, and so what we can do is okay there is again further maybe some comparison we can do. Okay, we can actually look at the coefficients, okay, in the top equation, okay, with respect to generic Gaussian distribution, because this is a general Gaussian distribution equation that we have seen, that is 1 by square root of sigma n exp of, okay, suppose, okay, because why we are actually using sigma n and mu n is actually we are say we associate that with respect to the the mean, okay. So that if you are comparing this equation 1, okay, and maybe this equation 2, suppose, okay, if you look into these two, we have a, okay, because here you have alpha, okay, so again you have a few things which comes into alpha, then exp, okay, then minus 1 by 2. So suppose you make a comparison, okay, we will get or you can actually get expressions for mu n and a sigma n square, okay. So that means we write a 1 by sigma n square is equal to, from just comparing the previous two equations and writing out, okay, these terms, okay, you can easily write down. And why we are actually trying to bring in, okay, mu cap is actually maybe the best mu value, okay, that we are actually trying to look for, okay. So that's why you have a say mu cap comes into picture. So that means if you rearrange the previous equation for mu n and maybe sigma n square, okay, so mu n and sigma n square, okay, so you'll get an equation of this kind, okay, you'll get an equation of this kind. So mu n is equal to, okay, this equation, okay, from this equation, okay, and sigma n square is actually of this form, okay. So this is just getting from this previous two equations. So the point is that so here if you look into these two equations, so we will get a very interesting point. Is one thing is, suppose if you look into sigma n square, okay, so the variance, so you look at what is sigma n square, how that is related to n. So n is, we know n is actually the number of samples, okay. So if you look into n and sigma n square, okay, so the variance actually decreases monotonically, okay, when n increases, okay. So that you'll get it, okay, an idea, okay. And so what is the significance is that when you are having say n increases, okay, so for different n value, we can say that the variance actually maybe say decreases. So that means you will get, say for example, if this is one probability of mu given d, okay, and another case for maybe say more number of, okay, n value, okay, number of samples, training samples are more, then you will get another of this kind. Then again, if you are increasing, then you will get something like this one, okay. So this graph actually shows maybe such a example. So we are actually plotting, okay, probability of mu given d, okay, because d is actually nothing but x1, x2, etc. up to xn, okay. And so here we are saying that this is mu, okay, along x-axis. And so you can see that here we are having only, say for example, so this is only maybe one number of training data, okay, suppose that is that the numbers represented. And that is one case where you have a very large variance, okay. So whenever you have a very large variance, you can say that whatever mu you have actually maybe taken from this one, okay, there will be a lot of difference, maybe, or there's a chance of error, okay, in prediction, okay. So that means you have there's a large deviation for, okay, the mean value, okay, and corresponding variance. Similarly, if you are increasing the number, okay, to 5, 20, okay, 10, sorry, 20 and 30, assume that you will be getting a curves of very high peak. And so that means your sigma square is actually reducing drastically as n increases. So that is this is in one dimension, and this is actually maybe a similar plot for maybe say in two dimension, okay. You can see that 5, okay, 24, then 30, so sorry, 50. So the point is that when the number of training samples increases, that means if you're having more training data, okay, then the error is going to be, or the variance, okay, is going to be drastically reduced, okay. And that will have a huge impact on the final decision that you are actually say making, okay. So whether So that is one point we have to keep in mind, that maybe whatever analysis what we have just discussed here is just to maybe finally conclude this very important point. Okay, that is going to be true with maybe in maybe basic learning, or maybe in this type of probabilistic say prediction. Okay, so that is one very important result. Okay, so far what we have actually trying to discover is probability of theta given t. Okay, so or maybe probability of mu given t. Okay, so once you're having but what we have to find out is ultimately probability of x given t. Okay, so that means assume that we have found out using probability of mu given t based on the previous discussion, and then we have to find out the probability of x given t. So but that is just an extension, or maybe we have already seen this equation, whether this is going to be in continuous case, or maybe for discrete cases. So we know that is probability of x given theta into probability of theta given t, because that was a equation that we started with. So here, suppose the theta is just mu, then probability of x given mu and probability of mu given t. So assume that we found out the mu given t using the previous equations. Okay, and then what we can say is that okay, there is some additions. So what we can say that this probability of x given t, okay, is going to also be a normal distribution. Okay, with we assume that there is a say so these are actually going to be, say, for example, the any prior information, okay, any prior information on the mean value, okay, that we have maybe found out using the previous method, will have some uncertainty. Okay, because all these are actually maybe using some guess, okay, or using some prior information, okay, or maybe with respect to the data set, whatever it is. Okay, but there can be some additional bias or uncertainty that can always be there. Okay, so that is actually maybe we are saying that okay, we have actually, say, for example, suppose sigma square is actually the original variance that we look for probability of x given t, but we assume that as we have already taken another probability distribution, okay, or with respect to probability of mu given t, so there is a variance there. So in the form of maybe say sigma n square. So that is going to be again uncertain. Okay, because that is going to be depending upon which mu value we have taken. Okay, so that is actually brought into maybe in the form of a term of uncertainty. Okay, maybe sigma square plus sigma n square. Okay, suppose that is why this representation comes. Okay, but ultimately we assume that okay, so we can actually combine, or we can apply this whatever principle that we have discussed. We can extend that, and we will be getting okay. Always there is an uncertainty, but if you are having more number of data, then or maybe depending upon whether the sigma n square is actually, if there is highly peaked, then your uncertainty is going to be very small, so that your whole result is going to be very good. So such but a point we can always keep in mind. So that is actually ultimately the Bayesian estimation actually works. We are trying to plot a probability, we are trying to find out a probability distribution for mu. Okay, and then we are trying to find out the best one, and based on that parameter value, we are trying to find out maybe the class conditional maybe density. Okay, so but here also we are trying to find out the maybe the best value, and the MLE also we are trying to find out the best value. The difference is here we are analyzing in the form of a probability distribution for theta itself. That means in this case mu that we have discussed. But in the earlier case we had not such a probability distribution based analysis, but we are trying to find out the best one. Okay, maybe a single value, because here you can have any value you can actually sample from the probability distribution of the parameters theta, and then you can choose the best one. Okay, so that may you can have a more freedom. Okay, more flexibility, more analysis can be done maybe in the case of Bayesian estimation, but that is actually limited in the case of maybe the first discussion that we have seen. Okay, so that is actually maybe some difference between these two. We will see one example maybe in the next class. So that means I think we will stop today.